This is lesson 2.3 on continuity. First, let's start with a brief definition of continuous. We say that a function is continuous if its graph can be sketched from beginning to end without having to lift your pencil. Now, of course, that's not the technical mathematical definition, but that's a pretty easy way to think of what continuous means. Let me show you a couple examples of things that are and are not continuous. So let's take the graph of like y equals 2x. That's a line, we know, something like that. That would be a continuous function. You could trace over this graph from beginning to end without having to lift your pencil. The graph of y equals 1 over x. That we've looked at several times. That looks like this. And we would say that would be discontinuous because you have this asymptote here that you had to jump over. Okay, y equals absolute value of x. Absolute value of x, remember, looks like a v. That would be continuous. Okay, one more. What if we have a piecewise function? Let's say we look at f of x equals 2x. If x is less than 0, and it equals x squared plus 1. If x is greater than or equal to 0. Right, so let's take a minute to sketch that for those of you that are having trouble maybe still graphing piecewise functions. Alright, so let's start with the graph of 2x, but we're only going to use that for x is less than 0. So start with 0. We'll substitute 0 in, we get 0, but because we're not equal to, we'll have an open circle at 0, 0. If I put in like x is negative 1, pick numbers less than 0, I get negative 2. Pick negative 2, I get negative 4. We now know the graph's going to go down like that. Then we'll graph x squared plus 1. But we're going to use it when x is greater than or equal to 0, so let's start with 0. If we put 0 in, we get 0, 1, closed dot, because we're allowed to equal 1 there. If we put in 1, 1 squared will be 1, plus 1 will be 2. If we put in 2, we get 2 squared is 4, plus 1 would be 5. We should know that that's going to be a parabola shifted up 1. So we look like that. And you can see that, that's definitely not a continuous function because we've got this gap right here. Matter of fact, the way I normally define continuous functions is that you want to look for something that has no holes, no gaps, and no breaks. So you're not going to have any holes in the graph or any gaps or any big jumps or breaks. Okay. Let's look at another piecewise function. I'll not give you the definition or the function definition. I'm just going to go ahead and graph it. Right here. Let's look at just a little bit. Let's say we've got a dot at 1, 1. An open circle at 0, 1. We've got another one. Or we're going to start at 0, 1. Sorry, not 1, 1. And then 1, 0, open circle, 1, 1, over to 1, 2, to 2, 1. Close dot at 2, 2. Then we're going to go to 3, 3. And down to 1. So we're looking at something like that. But if we have this graph, let's go back and make this an open circle here. If we have this graph, we have 3 points where this graph is, oops, let's connect those, where this graph would be discontinuous. We would say we would be discontinuous, in other words, not continuous, at x equals 1, at x equals 2, and at x equals 3. Now, the next thing I want to look at with you quickly is what types of discontinuities are there. We have 3 main different types of discontinuities. first type is what we call removable. And those are holes. Okay. If we go back to our previous example, you'll see I actually have two different types of removable discontinuities. We've got one here at 1, 0. Nope, sorry, that's not the removable one. We've got one at 2, 1. And we've got one at 3, 3. Next type of discontinuity that we would talk about is either a jump or a step discontinuity. And again, it kind of depends on whatever book that you're looking at, whether they call it jump discontinuity or step. That's the discontinuity we have right here at x equals 1. Because you'll notice that the graph jumps from being down here at 1, 0, and then the next place that you jump up to is at 1, 1. So we call that a removable or a jump discontinuity. And then the last discontinuity that we have, or that we're going to deal with, is an asymptote. We've talked about several of those. Oops. If we look at our graph of y equals 1 over x at the very beginning, here we've got two asymptotes. We've got a horizontal asymptote, and we also have a vertical asymptote. And we're going to be focusing on, when we're doing discontinuities, the vertical asymptotes. And so there's our three different types of discontinuities. When we talk about a continuous function, a continuous function is a function that is continuous at each point in the domain. So then the next thing we need to talk about is, what do we talk about when we're looking at being continuous at a point? Well, there actually is 3 steps to tell if something is continuous at a point. Some books call this the definition of continuity at a point. Some people call it the steps of continuity, or for continuity at a point. Our book actually calls it the definition of continuous at a point. Let's call that point C. So if you want to check to see if you are continuous at some point C, then there has to be 3 things that happen. First thing that has to happen is that the limit as x approaches C for f of x must exist. The second thing is that f of C must exist. And the third thing is that the limit as x approaches C of f of x has to equal f of C. And we'll look at what all that means here in just a moment. So here's our 3 things. Your limit has to exist. Your y value, that's what f of C is, has to exist. There has to actually be a dot at C. And then the last thing is the limit has to equal the y value, or you have to have the limit in the same place as where the dot's at. So let's kind of look at what happens if you would break those rules. So what does it look like if the limit doesn't exist? Well, that might be something like this. Here's where the limit, I'll call this point here C, as x approaches C, does not exist. In that case, then we could not be continuous at C. You'll notice there we have a jump discontinuity. And what about if f of C doesn't exist? Well, that might look something like this. Because if you notice, there's no dot at x equals C. We have that removable discontinuity, so there's no dot there. And then the last one would be, what would it look like if the limit as x approaches c would not equal f of c? So you kind of see what these are going to look like if they're discontinuous. Well, that might be the case where we've got this little there is our dot. Because in that case, the limit as x approaches c would actually be 1, but f of c would be 2. Now again, I want to stress these last two examples here, we call those removable discontinuities. When you just have a hole, those are removable, because the next thing we're going to look at is how can you take a function that does have a removable discontinuity and make it into a continuous function. Okay, let's look at a problem where we've got something like f of x equals x plus 3 and 4x. And we're going to equal x plus 3 if x is less than 1, and 4x if x is greater than 1. So let's look at that. See what the graph of that looks like quickly. And we're going to look at extending this equation so that it would be something that is continuous. And remember, the only way I can do that is if the graph happens to be have a removable discontinuity. So let's sketch the graph of this. Y equals x plus 3 if x is less than 1. So if I put 1 in, I'm going to get 4. So I've got a dot at 1, 4, but it's an open circle. If I put 2 in, or I'm sorry, 0 in, because I've got to pick numbers less than 1. If I put 0 in, I'm going to get 3. Negative 1 is going to give me 2, so I'm going to have that part of the graph. The second part, we're going to graph 4x, but we've got to do x is greater than 1, so let's start with 1. If I put 1 in, I'm going to get 4, and again, we're going to have an open circle there. If I put 2 in, we're going to get 8. It's going to be way up here off the screen, so it's going to do something like that. And what you'll notice is we just have a hole there in the middle. Well, if I could define where that hole's at, I could extend this function and say, hey, let's just add another part onto this, and let's make it a continuous function. Well, if I look, f of 1 is 4. So if I just say, hey, let's add that, we're going to let f of x equal 4 when x equals 1. That's going to come back, fill in our hole, and now we have a continuous function. Let's look at one more example with a piecewise function. So this time let's look at f of x is 2x minus 1 if x doesn't equal 2, and it's 5 if x equals 2. So again, let's just sketch that so we get an idea of what we're looking at. So we're going to graph 2x plus 1 for every number but 2. So let's start with 1. If I put 1 in there, I'm going to have 1. If I put 0 in there, I'm going to have negative 1. If I go back and put 2 in there, I would have 3. I have an open circle because I'm not allowed to use that. If I were to put 3 in there, I'd get 5. So what we're going to get the idea of is that our graph is actually a line with a hole. And this next part says we're going to let x be 5, or let y be 5 when x is 2. So we're just going to plot a point at 2, 5. So we've looked at several like this before, and so here's what's happening. We have a dot. Here's our example of where we have a limit as x approaches 2. As x approaches 2, our limit should be 3. But right now, f of 2 is 5, so we can't be continuous. So now what I'm going to do is I'm going to make a slight correction in this, and I'm going to say, hey, let's change this from let x be 5, or let y be 5 when x is 2, and change that to let y be 3 when x is 2. So if I make that change, that function is now continuous because that dot will come down here and plug in that hole, and we have a continuous function. Okay, Last thing we're going to look at also deals with piecewise. If you notice, we've actually done quite a bit of piecewise stuff when you're doing continuity, and that's pretty common. I want to look at how can I take a function that has maybe a k in it. You're going to love those problems. We usually kind of shut down when we see problems with k in it. And find the value of k that would make this function be continuous. All right, so first thing I need to realize is what I have here. This function is being made up of a line. 4x plus k is just a line. I just don't know what the y-intercept is. And x squared plus 3 is a parabola. So I've got a line and a parabola, and I want this function to be continuous. Now, lines on their own are continuous, and so are parabolas. So the only thing I have to worry about is, do these two connect to each other? Okay, does 4x plus k connect to x squared plus 3? If it does, then I know that I've got this thing to be continuous. So to make them to connect to each other, what we'll do is we'll just set them equal to each other. I want to know, when do those two things equal each other? Now here's the part that's important. They don't have to equal each other everywhere. They only have to equal each other right here at this point where they switch functions. So I'm going to put in let x be 2. That's the only time I need them to connect to each other. So if I put 2 in for all the x's, I get 4 times 2 plus k equals 2 squared plus 3. Well, that's 8 plus k equals 4 plus 3. So 8 plus k equals 7. Subtract 8. And I need k to be negative 1. So if I were to look at the graphs of 4x minus 1 and x squared plus 3, I would see that those two graphs would now connect at x is 2. And that's what I'm looking for. What values are going to make those be continuous? Okay, let's try one more of those. So let's say that f of x is the function 2x plus 5 when x is less than or equal to 3, and it's kx minus 2 when x is greater than 3. All right, so what I'm going to do then, again, we've got two functions that are linear. 2x plus 5 is a line. Kx minus 2 is a line. And the second one, I just don't know my slope. They're individually going to be continuous, so I want to make sure that they're going to connect to each other. Again, they don't have to equal each other all the time. They just have to equal each other right here at this point where they're supposed to connect. So I need to let x be 3. So if I put in 3, I get 2 times 3 plus 5 equals k times 3 minus 2. So that's going to be 6 plus 5 equals 3k minus 2. So 11 is 3k minus 2. Add 2. Don't panic if these don't turn out nice. They don't always do that. Later on, we'll find out we're probably doing something wrong if they end up being nice numbers. Divide by 3. So we need k to be 13 thirds. So if we go back and look at this, if I were to graph 2x plus 5 and 13 thirds x minus 2, I should see that those two graphs will connect to each other at x equals 3. Continuity is really not a bad concept. Again, just keep in mind that what we're talking about is to be continuous. Your graph has to be traceable from beginning to end without lifting your pencil. So that means you're not going to have any gaps and holes and breaks. Okay?